Hi, welcome to the screencast on. What we're going to do is finish up Vision, and then there'll be a separate screencast for hearing. As I recall, this is where we stopped, was the electrophysiology of rods. Now, the physiology that has to do with how the rods communicate with the bipolar cells and how the bipolar cells communicate with the ganglion cells gets pretty complicated. This slide here is kind of the long and short of the beginning. In the dark, rods are depolarized, which means if you're a neuron and you're depolarized, you're releasing neurotransmitter. When light hits them, they hyperpolarize. So if you're a neuron and you're hyperpolarized, you are not releasing neurotransmitter. And my slides are not advancing, and I don't know why. Oh, I bet I know why. There we go. I cannot have the draw feature and the cursor feature on at the same time. That is a bummer, because I don't like the cursor. At any rate, I'm not starting this thing over again, even though that was a little funky. So what you want to pay attention to on this slide is what's in black. So this part here and this part down there. Everything in between is a little funky. And more detail than you need to know. So we already said that in the dark the rods are depolarized and they're releasing neurotransmitter. You also need to know that in the dark the ganglion cells, which are the output cells for your retina, are not producing action potentials. So they are polarized or hyperpolarized or silent. So you still have this traditional no action potential in the output cell in the absence of light, but you've got this weird stuff going on in the middle. The reason why is that for reasons that are unknown to me, the bipolar cells, if left to their own devices, will spontaneously depolarize and release neurotransmitter. So what your rods then have to do is continuously release inhibitory neurotransmitter to keep the bipolar cells silent in the dark. And then when light hits the rods, we can actually go to the next thing. When light hits the rods, the bipolar cell will spontaneously depolarize because it's no longer being inhibited by the rod, and then the bipolar cell will excite the ganglion cell. So you still get excitation of a neuron in response to the stimulus. The ganglion cell gets excited in the presence of light, but it starts with this opposite of the way you would think it is situation where the receptor is hyperpolarized in the dark. Excuse me, depolarized in the dark, as it just says. Wow. And then they hyperpolarize in the light and stop releasing neurotransmitter so that the bipolar cells can be released from the inhibition, and then they activate the ganglion cells is how it's supposed to work. So they release a stimulatory neurotransmitter. Hopefully that all made sense. So then we look at specifically what's going on in the rods to control this depolarization, hyperpolarization. And it starts with this pigment called rhodopsin. Down here is one molecule of the pigment, which you would find embedded in all of the little sacs of membrane that are in the rod. So all up and down here, there would be, many hundreds of thousands of these opsin molecules, or excuse me, rhodopsin. Rhodopsin itself is composed of two different parts. The first part I'll talk about is second here. The opsin is a protein, and it's actually a G protein linked membrane receptor, which will become more clear when we do the endocrine system. For now, just know that this protein can make stuff happen. And it is what absorbs the light, and then it funnels the light energy into this red molecule in the middle, which is called retinol. The retinol exists in two forms, 11-cis retinol, which is what's bound to the opsin here, and then all trans retinol. And then this is just a bigger picture if you want to look at it. So then what we're going to do is talk about what's happening to the retinol and the opsin in the dark versus the light. And we're going to look at this picture here, but you can refer back to this text right here because that's what I'm going to be talking about. So in the dark, you have rhodopsin, which is the opsin plus the bent 11-cis retinol. When light hits the opsin, the energy is funneled to the retinol, causing a conversion from 11-cis to all trans. The all trans form is straight, and it doesn't fit anymore in the binding pocket of the opsin. When the opsin lets go of the retinol, this causes a brief hyperpolarization. And it's important that you remember that the hyperpolarization is brief in response to a certain amount of light. This is what shuts off neurotransmitter release. If this cell is going to hyperpolarize again, it needs to regenerate more of the opsin by converting the all trans retinol back into cis retinol. And this is what they have here. So for now, remember that this is what happens in the light, and it happens fast. And then when you regenerate your cis retinol, this is an enzymatic reaction, and it happens rather slowly. Let me see. I think that is, or those are, I should say, the major points for now. I will point out my one way to remember the difference between cis and trans retinol. So a C is curved or bent, and the the cis form of the molecule is bent. A T is relatively straight, and the trans form of the retinol is also relatively straight. So you've got your bent cis retinol and your straight trans retinol. So that is how things work in rods. Cones, we know, are pretty much the same way. There's a retinol type protein and then 3 different types of opsin, which is what gives your cones their ability to distinguish between different wavelengths of light or color. But the basics of the chemistry are the same, so we don't talk about it too much. All right, and then let's see, I included this in here again, and I don't remember why. So I guess this is why. So the next topic, we'll just go with the next topic and maybe we'll hop backwards or something. The next topic is called light adaptation. So this is what happens when you're moving from darkness into the light. So you're, let's go up here. You're here, right? You're in the dark, you move into the light. Because your rods are really sensitive, all of the rhodopsin is very quickly converted to opsin, and then it stays that way. How should I put it? Because the regeneration of the cis retinol is slow, your rods stay inactive with the trans retinol separate from the opsin the whole time you're in relatively bright light. So you're just relying on your cones. Oh, I'm sorry, getting all mixed up here. So all of your rhodopsin gets broken down. Your pupils constrict. The breaking down of all of your rhodopsin means that all of your rod pigments are bleached out, and your rods are functionally acting as if they're in the dark. And then once your cones warm up and that glare goes away, then your visual acuity starts to pick up in just a few minutes. It says here 5 to 10 minutes, but it's probably even quicker than that. So dark adaptation then is exactly the opposite. So you're in the light, moving into the dark. The first thing that's going to happen, or the easiest thing to think of, is that your pupils dilate. When you are in the dark, your cones cannot function. So when you are first in the dark, your vision is not very good because all of your retinol is in this 11 cis shape, and it has to be converted back to the all trans retinol. So if we look here, you're moving from the light into the dark. Your cones are inactive and unable to respond to these low light levels. All of your rods are in this state right here with opsin plus the transretinol, and you need to regenerate all of the rhodopsin. This takes time. So that's why when you first turn off the light, when you go to bed, you don't see very much in your bedroom. And then if 20 minutes later you have to get up to pee, which is really annoying because you just got in bed 20 minutes ago, but whatever, it happens, right? So you get up after being in bed for only 20 minutes, and all of a sudden now you can see a lot better because this whole time your eyes have been closed. Your rods have been making rhodopsin, and there hasn't been a lot of light around to bleach out the rhodopsin, so you've got a lot of it, and your cones become very sensitive. Hopefully that makes sense. That tends to be one of the things that confuses people a lot. So I think you just have to sit there and look at this figure and work your way through light adaptation and dark adaptation. The visual pathway, you can look at these words while I show you this picture right here. So for the neurological pathway, you want to remember that at the cellular level, it actually starts with your photoreceptors. So within the eye, the photoreceptors get activated. They communicate with the bipolar cells. The bipolar cells communicate with the ganglion cells. And then it is the axons of the ganglion cells that make up the optic nerve. And then the optic nerve projects back to either side here of the thalamus, a special place of the thalamus called the LGN, or lateral geniculate nucleus. You can just call it the thalamus. So the axons of the ganglion cells end at the thalamus and dump neurotransmitter onto another group of cells. That group of cells projects back to the occipital lobe, and collectively that group of axons is called your optic radiation. So from excitation of a rod to the sensation of an image in your visual cortex, it's going to be rod, cone, bipolar cell, ganglion cell, optic nerve, thalamus, optic radiation, primary visual cortex. That is your primary visual pathway. Then, of course, there are offshoots that don't have to do as much with the perception of images, but visual reflexes and your brain's awareness of how often you're in the light versus the dark. So your midbrain is made aware of light and motion to initiate visual reflexes. This is controlling things like the movement of your eye to track objects in your peripheral view, or dilation and constriction of your pupils. And then your hypothalamus is made aware of just how much light you're exposed to throughout the course of the day. And that's what, in many animals, not so much humans, but in a lot of animals, that's what sets their daily biorhythms. So their behaviors change from season to season. When they're mating, when they're eating, maybe when they're hibernating. And the cue that they're picking up on that you're moving from summer into fall is that days are getting shorter. And then in the spring, days are getting longer. So your brain tracks day length and knows kind of which part of the year you're in. Depth perception, this is our last slide for understanding the last bit of vision. And what you need to know is that each of your two eyes looks at the world from a slightly different angle. And what your brain does is take the difference between what's coming from the left eye and what's coming from the right eye and merges those two together to give you a three-dimensional view of the world, so that you're looking at everything from two different perspectives. And it's those two perspectives that allow you to judge distance and depth and all of that better. So that's it, just about 15 minutes to finish up vision. Keep an eye on your email inbox for information on what's the next part? Hearing. That's it.